Statistics and Bioinformatics in Bonn, Germany, and he's going to talk about the GestaltMatcher, identifying the second patients of its kind in phenotype space.
Thanks for the introduction and thanks for the great opportunity to be here. Hello everyone, and before we start, please just imagine you are a genetic doctor today and you have a patient with the phenotype you haven't seen before. Then maybe you wonder, where I can find another patient with this phenotype, because I want to analyze them together because it is too difficult to diagnose this disease with only one patient. So therefore, today I would like to introduce how we utilize the next generation phenotyping approach to identify the second patient with the same rare Mendelian disorder in this world. And I have no conflict of interest. And with the recent advances in computer vision and machine learning, the next generation phenotyping approach has become very popular for syndromology. It enables us to learn the facial representations by training on patients' photos. So by this approach, we can first quantify the similarity between the patients to the phenotype, and then help us to diagnose the patients. So for example, here we have a patient with Cohen-Cyrus 1, and by analyzing his photos, then we find out the most similar syndromes here is Cohen-Cyrus 1. And then we know that it is ARID1B which caused this disease. So we further check the mutations in ARID1B and find out the disease-causing mutation. So by this way, the NGP tool is very effective for the diagnostic workup because it helps us to narrow down the candidate genes. And until now, there are several studies utilizing the NGP tool to analyze the Mendelian disorder. So here I will list the most famous two studies. So the first one is from Ferry in 2014. They collect more than 1,000 patients' photos and analyze on 8 different syndromes. They are almost the first one who conduct the facial analysis on such a huge cohort. And until now, this 2019, this January, the facial analysis tool Deep Gestalt, which is behind the Face2Gene platform, was published on Nature Medicine. They trained a model on more than 17,000 patients' photos and 216 syndromes. They achieved very high accuracy and even outperformed some human experts in certain classification tasks. And although the Deep Gestalt performed very well on syndrome prediction, but we still wonder what if the extreme rare disorder or the novel disease is not supported yet due to lack of the patient's image. So for example, the model cannot recognize the disease on these patients because this disease is too rare and we don't have enough photos to learn the facial representations. Then of course we cannot diagnose this patient. And moreover, the annual study from the OFNET shows the imbalance between the estimation of the prevalence and the number of the rare disease. So in this figure, the x-axis is the prevalence of the disease and the y-axis is the number of the disease. And here we can see that when the prevalence becomes lower and the number of the disease increases dramatically. So therefore, it is very difficult for us to support more rare disorder if we are not able to find out more patients in this world. So therefore, in our study, to explore more patients with the rare disorder, we would like to match the patients with high similarity of the facial dysmorphic features. So here I would like to propose the GestaltMatcher, which we quantify the similarity between the patients and further find out the most similar patients in the database. Then the clinicians are able to contact to each other and further discuss the similar mutation and diagnose the patients together. And here I would like to introduce a related work from Judin in 2017. They utilized the computer face matching technology to match the patients with 10 intellectual disability syndromes. They are almost the first one who proposed this idea, but they only focus on the syndromes with intellectual disability. And this is the data set we use in our analysis. So first, we use the 679 cases from our PDA consortium, which cover the 103 monogenic disorder and as a testing set. Then for the training set, we took more than 20,000 patients' photos from Face2Gene database to train our model. And then I would like to introduce how we extract the facial features from the patient's images. So first of all, we trained the deep convolutional neural network on 20,000 patients' photos over 300 syndromes. Then we further put the testing image into the network and output 216 dimension facial embeddings from the photos, and further span the clinical face phenotype space by these 216 dimension vectors. And in the clinical face phenotype space, the similarity between two patients is quantified by the Euclidean distance between two patients in the space. Then we further want to prove that if the patients are close in the space, do they have similar phenotype? And here is the workflow of our GestaltMatcher analysis. So first of all, we train the network by the 20,000 patients' photos, and further we put the testing image into the network and extract the facial embeddings and further span the clinical face phenotype space. Then we further perform the pairwise comparison to calculate the distance between each patient. And in the end, we can simply sort the patients by the distance between each other to find out the similar patients. And for example, here to the testing image on the left, these are the three patients with the top three nearest patients in the testing set. So it means that these are the most similar three patients to this testing image in the test set. And how we evaluate the performance. So here we have a patient with Coven Cyrus 1. So if the nearest patients in the space also have Coven Cyrus 1, then we call it top 1 match. And here we have a patient with Noonan syndrome. If there is another patient also have Noonan syndrome and is in the 5th position or better than 5th position, then we call it top 5 match. And it also applies to top 10 or top 30 match. And here I would like to show you the first result, which is the accuracy of from top 1 to top 10 match. And here you can see that the top 1 match is 51% and top 10 match is 82%. It means that if I upload a new patient, the patient's photos, then the chance to have another patient with the same phenotype in the top 10 nearest patients is 82%. And then we look at the box plot on the right, which is the pairwise distance distribution comparisons. So here the y-axis is the distance between two patients, and the left one is the distance between two patients with the same syndrome. The right one is the distance between two patients with different syndromes. And here we can see that the distance between the patients with the same syndromes is clearly smaller than the distance between the patients with different syndromes. And moreover, maybe you wonder how the patient distributes in the space. So in order to show the visualization, so here I select the patients with three syndromes here, the Coven Cyrus, HPMRS, and Noonan syndrome. And further, we perform the t-SNE to map the patients into 2 dimensions. So here you can see that the patients with the same syndrome cluster together and form the 3 clear clusters here. So it means that the patients with the similar syndromes cluster to each other in the clinical face phenotype space. And moreover, I would like to introduce the facial analysis we performed in the recent published paper from our collaborator in Cologne. So these are the 2 unrelated patients with unknown diagnosis from 2 different countries. They both have the Bulgaria-like dysmorphic features and later identified the same de novo disease-causing mutation in LEMD2 genes. And originally, these 2 patients were matched by the GestaltMatcher. And in our analysis, we found that these 2 patients are both the nearest patients to each other in the space. So it means that we could also utilize the GestaltMatcher to match these 2 patients by the facial photos in the space. And then if the patient can match in the space by the facial photos, then the clinician can contact to each other and discuss the similar mutation and further to explore the unknown genotype-phenotype association. So I think some of you might be already familiar with GestaltMatcher, which is widely used for match the patients by the genomic data. So here you can think of the GestaltMatcher is a facial image version of the GestaltMatcher. So and if you like our study and would like to join us, so please go to your patients page in Face2Gene platform and simply check the patients matching box here. Then once we have the matched patients, the clinician will be put in contact to each other. And of course, only the unidentified data will be shared. No one is allowed to access the photos, including us. And in conclusion, from the results above, we know that a Gestalt matching approach is able to match the patients in the clinical phase phenotype space. And however, we still have some future plan. We would like to perform some more comprehensive benchmarking with some well-known facial recognition approach like the ArcFace or FaceNet. And moreover, with the current data we have, the confounding factors such as the ethnic background and the ages will not be able to be analyzed yet. And in the end, if you like our study and would like to join us, and we could explore more unsolved cases and unsolved disorder together and further contribute to this society. And in the end, I would like to thank to my supervisor and all the colleagues in IGSB and FDNA and Charité Berlin, and thank you.
Open for questions. Yeah.
Hello. Thank you very much. I think this is very important to have. So I'm wondering, the usefulness or all this approach basically depends on the size of the database of all the photos that you have. Can you maybe comment, like, can you access photos from other countries, and what's the collaboration regarding the change of the photos of images of patients?
Yes, actually, the majority of the data is from Caucasian, from the European. Yeah, and now we would like to explore more collaborator to get more data from different countries, like maybe from Asia, because now I think the ethnic background still is a very strong compounding factor. So we need to explore more patients from different backgrounds to analyze this data.
And is this data Germany-based or it's Europe-based or?
I think most of data from Europe and also a lot of data from America. Yeah, but still some data from Asia.
Okay.
I'm Max Schuber from Berlin. So I was wondering how many patients of the same syndrome do you need in your training set to find a new relation of a new picture?
Actually, now I think we need to have maybe around 10 patients. But in theory, the goal is that we want to match the patients with this. We want to match we want to support if we can only match patients, only one patient in the database with the same phenotype.
I get it's cool to do this entirely based on the image, but really if you want to find another patient with the same diagnosis, then it would make sense to also incorporate other clinical information as well. And obviously that could sometimes be very helpful in terms of finding matching patients. So I'm wondering whether you could sort of add to your machine learning some clinical features as well as just the image.
Yes, actually, we also think about that, but now because we still have to improve our image analysis, so I think that will be the next step to do it.
Hi, Maria from University of Cologne here. I will actually extend the last question. I was wondering if you would add the phenotype of hands and legs as well, or back. It might add more information to validate the syndrome along with the facial features.
Yes, actually we have some colleagues doing that, so I think once they have some promising results, then we can integrate together.
Okay, thank you.
All right, so then this concludes our session. Let's thank all the speakers one last time.